Welcome to my new lecture or video. Now we are going to do a full wave bridge rectifier in Proteus. In my last tutorial I said I'm gonna do a full wave center tap rectifier, but I'm not gonna do that because there's some problems for me in Proteus, so I'm not gonna do that. I'm just gonna skip to the full wave bridge rectifier that is more commonly used than the full wave center tap rectifier. So basically, here is how a full wave bridge rectifier looks like. We have four diodes uh, that are organized like this, and we have a transformer. The transformer's job is to lower the voltage from the input to the output, from the primary side to the secondary, from 120 volts to 10 volts, or if you're in Europe, from 230 volts to 10 volts. Uh, Now, here is how it looks. We have a Here is how it goes. Here we have an AC line that we all have in our plugins at our home. We have a sinusoidal changing our alternating current, and on the outside we are gonna have this pulsating DC. I'm not gonna use an oscilloscope for this because it's kind of hard to use an oscilloscope in Proteus. You just have to believe me that this is how it is changed in here into the output. So go to your Proteus, or you can just watch me how I'm going to do it. Go to your library. First, I'm just gonna take a bridge. Just type in bridge, and you will get a generic bridge rectifier. There are a lot of types of bridge rectifiers for various types of volts and amperes. I'm just gonna take a general bridge. So now I'm gonna take a sinusoidal power source, and that's it for now. Oh, I can take a transformer. I got a transformer, ideal transformer. I don't know, maybe a LED, yellow LED, light emitting diode, uh, capacitor, maybe. I'm gonna take an animated capacitor. What else? A resistor, and that's not in all categories. I'm just gonna take a resistor here. Okay, so first I'm gonna show you the working principle of a bridge rectifier. Here it looks like this. I'm gonna put a sinusoidal voltage source, and I'm just gonna connect a one side to this here, and one here. Now here is the output. It's gonna be a DC output. I'm just gonna put a frequency of 1 hertz. One amplitude can be 1 for now, and the frequency can be 1 also. Just let me set an animation option. Okay, it's all good. Now when sorry, just wait to simulate the program. Okay, take some time to run the program. Oh, sorry, okay. Now I'm just gonna pause it in one. So this is how this is how it goes. Here we have an alternating current. The current in this situation goes from here here. Current is not gonna pass here because it goes into the cathode of the diode, so it blocks here, but it can go here. Now the current won't go here because in this particular diode, because it would go into the cathode, so it blocks it. Then the only path it can go is from here, here. Just follow the pencil, and it can't go here because it's already been blocked, but it can go into this diode, and it goes to the in this particular moment to the negative side of the battery. Now this is the second situation when the current is going to the other side. As you can see, from this point to this point, the current stays the same. Now current goes here, this diode blocks it, but it can go to here, and then the current goes here, 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 and it goes through here, and now the negative side is here on the higher upper side of the voltage source, and as you can see here, the current will always be the same no matter what. You can just watch this point. Just watch now when I run the program this side. It always goes into the from this point to this point. Although the current is changing from here in this circuit, but it always is going in this direction. The current is, pulsating because it's a sinusoidal. It goes like this. But if we put a capacitor, it can, it can a little bit filter it, and then we would have a steady voltage. But now I'm gonna show you a practical way how it is done with a transformer. We use transformers to lower the voltage, because in our households we have an AC power supply of about I don't know, in Europe it's 230, and in America I think it is 120. So I'm gonna put a sinusoidal here. It would always be good to put a fuse to prevent, as you can see, in practice it's always good to use a fuse. For example, 250 volts and 2 amperes, but I'm not gonna do it now. I'm just gonna show you educational. Also, my advice, if you haven't done this already, if you're not experienced, please do this project with a professor or an experienced engineer. It's very dangerous. It's very dangerous to do it by yourself if you're not experienced with the transformers, because the voltage here is very high. So now we're gonna put, I don't know, RMS of, I don't know, we can put 230 or 120. It doesn't matter for me. 50 or 60 hertz also. It also depends where you are. So here the turn ratio then must be 12. So then there will be 10 volts on the secondary side. I explained that in my previous lecture. Now I'm gonna just put like this. Okay, now I need a bridge rectifier. Okay, now go here, take a bridge rectifier. Now this side goes to the higher side of the secondary side of the transformer, and it goes here. Now and this side, now like this, here we will have a pulsating DC. So let me just put the LED. Well, if I put the LED, let's bring this to 1 Hertz just to simulate the program. Now I hope it will run the program. Just a second. I hope there won't be no errors. I mean, yeah, time step is too small. I don't know. Let's make it already 60 Hertz. It says it's not good. Well, I don't know. Okay, so no matter. I'm just gonna put a resistor here. I'm gonna do it practically. Then I'm gonna put a resistor here. It can be 10K. I don't know. Nothing special. I'm gonna put an LED right here. Okay. Goes like this. I'm gonna put a capacitor. it should work now, but also I don't know if it's gonna work. So let me simulate to run the program. Also, I don't know what's the problem. It says stepping at time. I don't know. Not 0.222. What if I just take out this LED? Yeah, so maybe the LED was a problem, I don't know. But here now you can see that you have a DC output. And yeah, that's kind of, this is like the some kind, this is like the practical way. But also there you have to put a fuse over here. If you want to measure the if you want to change, if you want to see how it is done with an oscilloscope, well, okay, I'll do it, but I don't guarantee that it will work for me. So I'm gonna put here an input, and I'm gonna put on the green one the output right over here. So if I run the program, just a minute, I hope it's gonna be all right. I'm gonna put here 0. I'm gonna turn this one. I'm gonna turn this one out, and let me just take a time. Okay, so here you have the output, but I don't know. It doesn't show the best way. Shouldn't be like this, but okay, I just show you. Here is the input, and here is the filtrated output. But also you have to measure the time step and the voltage. I mean, it's kind of hard with this digital oscilloscope. It's might much more better if you do it in real life than in this Proteus. I really don't like to work with oscilloscope in this program, but you know, it's kind of sloppy, if I have to say it like that. Okay, so this is the full bridge rectifier. This capacitor stores the charge, and uh, you will always have an DC output over here. I don't know, maybe if I put a DC motor, DC, I'm just gonna undo this, delete this. Now I'm gonna put a DC motor right here. I think it should I think it should have a steady uh, clockwise rotation. So when I run the program, it doesn't rotate because I think that lower the value for some kind of, maybe this is, yeah, pretty high. 6. Now let's see how it's gonna, yeah, the motor is not, put a 5, yeah, it's really small. I don't know the meaning Cristo. Okay, I don't care. But I think you understand now the basic principle of this full wave bridge rectifier. I hope I explained it good. So thank you very much and see you in my next tutorial.